It's not rocket science, but it is exercise science. And I think when we build programs, we need to think more like scientists. So the purpose of this very brief tutorial slash lecture is a scientist's guide to program design. So the discussion points for today, thinking like a scientist. So I want to start by defining logic because I think that goes a long way in explaining how we come to conclusions as human beings, specifically the difference between inductive reasoning and deductive reasoning. I want to talk about the experiment and the variables that go into it. I think as strength and conditioning coaches, as performance coaches, what we're doing is conducting a temporary hypothesis or an experiment, and those experiments have different variables. I think it's important that we know how to define those variables and what to look for when we manipulate those variables. And last but not least, the conclusion. So let's get started. Thinking like a scientist. How do we as a human species reach conclusions? Well, I think before we get into that, we need to define logic. So logic is the science of valid inference. And what I mean by inference is conclusion. How we draw conclusions stems from a premise. We need to think about premises as a starting point. Data, a objective mix and subjective mix of information. And when we have a premise and a conclusion, we draw conclusions two different ways. We do it inductively and deductively. We'll briefly speak about both, but I think for the purpose of this lecture and thinking like a scientist, deductive reasoning is where we'll steer this conversation towards. So inductive reasoning, it formulates a premise from repeated experience. Okay, so this is something that for strength and conditioning, I could give an example. Perhaps we've witnessed 10 different coaches squat their athletes, and every single athlete's vertical jump has improved. So we may make the broad-based inference that all squatting improves vertical jump. This is inductive reasoning. This creates mental shortcuts called heuristics. These allow us to make decisions quickly, and basically they move beyond the premise. Another example I could give you is if this swan is white, that swan is white, the next swan is white, well, therefore all swans are white. Again, here we're moving from very specific experience to something very universal, which is a hypothesis. Now, I'm not knocking this form of thinking and reasoning because the reality is I think we all use it every day, but I also think it can get us into trouble as coaches, right? Well, just because other coaches are doing something certainly doesn't mean it's right. That's not thinking critically. Just because a mentor says something doesn't mean that it is appropriate. Everybody's fallible. So how can we think better and be better critical thinkers when it comes to designing our programming? Hence, deductive reasoning. Here, it starts with a problem. Sir Karl Popper, who we'll see in the preceding slide, is famous for saying science starts and ends with problems. So for deductive reasoning, there has to be a rationalistic approach, meaning what's the problem? From there, we formulate a premise or a hypothesis, and we gather data. We measure, we experiment, we infer. And when we think deductively, we don't move beyond the premise. Again, this stems from a very universal thought, so a hypothesis or a temporary theory. We error eliminate and we get to a specific result. When thinking deductively, we also know that what works for one sample size or one athlete certainly may not work for every athlete. So we do not move beyond the premise and make broad assumptions from experience. Rather, we start with a problem. That's a critical distinction between deductive and inductive reasoning. This is the schema that we use at Donskov Strength and Conditioning when we design programs. And up there, again, in the top left, you'll see a very, very famous and very smart scientist/philosopher of the 20th century, Karl Popper. This is his schema of conjectures and refutations from his book, Objective Knowledge. Here we start with a problem. For a strength and conditioning coach, it would be how do we design a program for athlete X? How do we design an energy system means for athlete X? How do we design a return to play for team Y, etc.? From there, we gather information, both the existing literature, our objective information that we've gathered thus far, and our subjective hunches, and we create a temporary theory. Again, this isn't proven science. It's simply a theory that we're going to test. We do this by measuring and managing and setting KPIs, and then we error eliminate. This is an important process that I think we all can do a better job of. How do we error eliminate? We get feedback from coaches. We get feedback from our athletes. We measure our KPIs. Is the needle moving the right way? Is it not? And from there, a new problem arises. So this is a continuous negative feedback loop, if you will, of thinking like a scientist. So essentially, we're using, as Popper would say, critical rationalism. We're starting and ending with a problem. This is how we design our programs at our facility. The experiment. Yes, every one of our programs is a scientific experiment. I think it's time that we think more like scientists, and in my opinion, this is how we do so. If you think of an experiment as a cause and effect proposition, the cause is the independent variable. That is what we intentionally try to change to test the effect of the dependent variable. The effect here is the dependent variable. Okay, so let's explain that a little bit more in lay terms. Okay, independent variable. Again, what are we trying to change as coaches? Here it's the acute programming variables. When I think of acute programming variables for coaching, I think of what we manage and measure on the floor for program design. So exercise selection, rest, the number of sets and the intensity that we used. These are all our independent variables. And how do we progress those independent variables? We can do it one of three ways. We can do that by progressively loading the athlete, so progressive overload. We can do that by variation, adding different forms of exercises to tax different motor unit pools. And we can also do that by specificity, being much more specific to the demands of the given sport. Okay? The dependent variable here is the athlete and the adaptation that we're trying to solicit. So independent variable is our acute programming parameters, and our dependent variable is the athlete. I think John Kiley did a fantastic job of articulating this in his paper, 21st Century Periodization. It's important that we as coaches periodize the proper input, or the proper variable rather. We're trying to periodize here not the independent variable by looking at a piece of paper, but we're trying to periodize the response from the dependent variable, which is the athlete in this case. Okay, so another take-home point for me on this slide is in any scientific experiment, we're really trying to control the amount of independent variables. If we change too many things too fast, too often, we have no clue what works and what doesn't work. Variety can be a slippery slope at times. Again, I know this can be dependent on the time of year, how much time we have with athletes, but when we're thinking like scientists, it's not how much can we add to the experiment, it's how much can we control and how much can we really hone in on to see if it works or if it doesn't. Conclusion, golly, I wish I could say there was a right answer, but the reality is there is no right answer. You can get there different ways and you can get closer to the truth. 8 plus 2 is 10 and so is 2 plus 8. You can get there different ways. Karl Popper would say a scientific result cannot be justified. It can only be criticized and tested. The role of the scientist is to provide a temporary hypothesis and to constantly try to poke holes in that hypothesis, essentially getting closer and closer to the truth. So when we think like a critical rationalist or when we think deductively, we start with a problem, we create a theory, we test that, we measure that, we have KPIs, we try to poke holes in it, we error eliminate, and then a new problem arises. As opposed to the line of inductive reasoning, which creates mental shortcuts or heuristics. These are great. Certainly we add these to programming as well, but the goal here is to think more like a scientist. It takes more time, and it starts and ends with a problem. Hope you enjoyed this brief presentation.